In this video, we will be solving a linear program involving 2 variables and 3 constraints. In order to graph it, we need to first find the endpoints of the constraint lines. So on the first one, we'll set x equal to 0. So then we have 14y is less than or equal to 84. So dividing both sides by 14, we get that y must be 6. And then when we set y equal to 0, we have 12x is less than or equal to 84. So that must mean that x is equal to 7. On our second constraint, we set x equal to 0. And we have 2y is less than or equal to 19. So y is equal to 9. And then when we set y equal to 0, we have 3x equals 18. So x equals 6. And then on our third constraint, y is less than or equal to 5. It just means no matter what, y is just always equal to 5. Okay, now that we have found the endpoints, let's graph them. Looking at the y values, I've got a 6 and a 9 and a 5. So the biggest thing I need to graph is a 9. So if that's 9, we'll call that 6. We'll call that 3, approximately scale. Then looking at the x's, I've got a 7 and a 6. So let's call that 8, 4, 6, 2. Okay, first constraint. I don't know how well the colors pick up, but I'm doing this in blue. So x equals 0, y equals 6 will be right there. X equals 7, y equals 0. That will be down there. Draw an approximately straight line. And it's less than or equal to, so we have to be below that blue line. Second constraint here. X equals 0, y equals 9. That'll be up here. X equals 6, y equals 0. That'll be down here. And we'll get something like that. That's not very straight. Sorry about that. And it's less than or equal to, so we have to be below that constraint. Just a little note here. If you can draw straight lines, you're going to find your intersection points pretty accurately. Mine's going to be a little off probably because of my wonky line there. And then lastly, y is less than or equal to 5. So if this is 3, that's 4, that's 5. So straight line right there. And then we have to be below all 3 of those lines. And then we have non-negativity constraints here. So we have to be on this side of the y-axis, which is what prevents x from going negative. And then y cannot go negative, which means that the horizontal axis is also a constraint. So our feasible region is this area down here. And we know that the optimal solution has to be at a corner point. So that is a corner point, and that is a corner point, and that is a corner point, and that is a corner point. However, these 2 points have the exact same y value because this is a perfectly horizontal line. And the second one here has more x. So this is just not interesting. There's no way that could be optimal. So we have 3 points that we need to investigate. The first one down here, that was one of the endpoints of our orange constraint. So that was the point 6, 0. Now the other 2 we have to solve for. So let's figure those out. So I don't know, let's do the intersection of the orange one and the blue one. So the blue one is 12x plus 14y. And then when we are on the constraint, it is an equality. And so that's the blue line. And then the orange constraint is 3x plus 2y is equal to 18. So I need to multiply something by something to try to get something to cancel. Easiest way forward to me here seems to be, I'm going to multiply the bottom one by 4 so that I get a 12 in front of the x's. So multiplying this whole row. So 4 times that whole row. So that will give me 12x plus 8y equals 72. So then I'm going to take the top one and subtract this bottom one, 12x minus 12x, 0x, it just goes away. 14y minus 8y gives me 6y. And then 84 minus 72 gives me 12. So y equals 2. Like I said, that's supposed to be 2. My wonky line is hurting me there. So I know y equals 2. So I can stick it in for anything. And the easiest way forward to me seems to be to put it into that second constraint. So we have 3x plus 2y. So y is 2. So that's just 4 is equal to 18. So subtracting 4 from both sides, we get 3x equals 14. So dividing both sides by 3, we get x equals 4.67. So we have found this point right here. This is the point where x equals 4.67 and y equals 2. Yeah. Can't prove it by my graph. Like I said, straight lines that help you out. Okay, so then lastly, we need to find where the blue line intersects with the red line. So let's see. The blue line, that is our top one, 12x plus 14y. So let's do that here. So 12x, x plus 14y equals 84. And then the red line just says y equals 5. All right, this is going to be easy. That's why I saved this one for last. So we just put a 5 in for that. So we get 12x plus 14 times y, and y is 5. So 14 times 5 is 70 equals 84. So subtract 70 out both sides, and we get 12x equals 14. So x equals 1.17. Okay, so we've got that point as well. So this is the point where x equals 1.17 and y equals 5. Okay, so we've got the 3 points identified. We need to figure out which one is going to be the most profitable. Now, we could draw an isoprofit line. I'm going to skip that step, but I am going to point out here that the x's are 3 times as valuable as the y's. So that makes me think it's not going to be this one, probably not going to be that one. My money is on this one down here in the corner, but let's try it out and see what we get. Now, as you probably know, we sometimes refer to the objective function by calling it z. Why? I don't know, but it's handy. So we will evaluate z at these 3 points. So when we look at z at 1.17 and 5, we get 3 times 1.17 plus 5. And so that is 8.51 as our first point. Now, if we look at the second point, z evaluated at 4.67 and 2. So we have 3 times 4.67 plus 2, that's a plus 2 times 5. So 3 times 4.67 is 12, 13, 14. Plus, oh, I'm sorry. Is that right? It's just, I don't know where I got that 5 from. I was getting ahead of myself. Y, oh, I looked wrong. Y is just 2. So we have 14 plus 2. We get 16 as our objective function there. And then lastly, when we evaluate z down at the bottom, where we have 6 and 0, we have 3 times 6 plus 0. So we get 18. So out of these 3, obviously 18 is the most, and we're trying to maximize profits. So that is our answer. So the optimal decision is for X to be 6, Y to be 0, and the profits we receive from this will be 18. So just to recap, we had the linear program in standard form. We found the endpoints of each constraint. We then drew the constraint on our graph. We figured out which intersection points were worth solving for. Then we went and solved for them. And then we evaluated the objective function at each of those points. And we selected as our winner the profit that was maximized and the point that got us there. So there you go. I hope this has been helpful.